In this video, we'll define the loss function we'll be using for training neural networks. So we've seen the stochastic gradient descent algorithm. So in this video, we're talking about defining this loss function here that we need as an ingredient for performing stochastic gradient descent. So we know that a neural network, for classification, we can think of the output layer as giving us an estimate of given some input, what is the probability that it belongs to class C? What is the probability that the y, the target associated with x, is actually equal to some given class C? So f of x, capital F of x, which is the output layer of our neural network, that's a vector. And so the Cth element would give us the probability that x belongs to the Cth class, and the whole vector gives us the whole distribution, conditional distribution of what the target could be given x as estimated by the neural network. So something that would be fairly intuitive would be to maximize the probability of the correct target yt given some given input xt from our training set. Now we are framing our training as a minimization problem, not as a maximization problem. So we'll convert this problem maximizing the probabilities into a minimization by using what is known as the negative log likelihood. So the negative log likelihood is so L of f of x and y, where x is the input and y is the true target, is going to be minus the log, and it's going to be the natural log. I'll use still log even though sometimes we write ln for the natural log. So it's going to be minus log the yth element of my output layer. Yth because this is the y here, so this is the actual true target. So I'm going to minimize minus log of the yth element of the output layer, which is the estimate of x belonging to label y. Because log is so the relationship between maximizing the probability and minimizing the negative log prob is that maximizing something is the same thing as maximizing the log of something, because log is a monotonically increasing function. And then maximizing something is the same thing as minimizing the negative of something. Okay, so these two problems are actually equivalent. Another way of writing the negative log likelihood is as follows: minus the sum over all possible classes C of the an identity function, which is 1 if y, which is the true target, is equal to C, this index over which I'm summing. And then so this identity function is 1 if this is true and 0 otherwise. So if y is equal to C, then I multiply 1 by the log of f of x of C, which is my estimate of the probability of the true class being C. And otherwise, if y is not equal to C, then this term is 0, so this term disappears. So effectively it means that, the only non-zero term is this one. So that's why these two things are equal. So we take the log to simplify and also to get some numerical stability. So we take the log to get some numerical stability and also to simplify the math when we're going to compute in particular derivatives of the parameters. And this loss is also known as the cross entropy. So if you're familiar with, if you know a little bit about information theory, the cross entropy between two distributions is actually takes this form. So in fact, this would be the cross entropy with the minus, would be the cross entropy between this distribution here, which puts a probability of 1 over the true class and 0 over all other class. So the cross entropy between this distribution and that distribution, which is the distribution that is output by our neural network. So this is going to be the loss function we'll use for training our neural